at the DIS conference. The conference is hosted by the Center for Frontiers in Nuclear Science in Stony Brook University. At Stony Brook, it's currently 8 a.m. in the morning. So good morning to everyone in the US, and good afternoon to everyone in Europe and Asia. The presentations will be for invited talks, 20 minutes plus 5 minutes for discussion, and for the contributed talks, 15 minutes plus 3 minutes for discussion. We really would like to have some discussion time, so I will give you all a reminder 5 minutes before the end of your presentation, just as some guidance. And I will then also let you know when the nominal speaking time is over. We are currently only 15 in the session, so let me maybe wait 1 more minute or 2 more minutes for more to join. Our first talk is an invited talk. Marco Battaglieri from Jefferson Lab, he will give us an update on the CLAS12 experiment. This is a large 4-pi spectrometer at Jefferson Lab. And so let's hope that there will be a good turnout for his presentation. So far we stay stable. Marco, I would say let's start, and let's hope that then in the next minutes more will join. I'm really looking forward to your update on CLAS12.
Okay, so first of all, let me thank the organizer for this invitation. Give me the occasion to present present and future CLAS12 physics program. So let's go immediately to Jefferson Lab. This is the primary electron beam up to 12 GeV in the region of lambda is the length, the wavelength of the electron that or the virtual photon that is exchanged goes in the region between the nucleon and the quark transition. So this is exactly the energy that you want to have to map out the degree of freedom transition between quarks and hadrons. The characteristics of the beam is 100% duty factor that provide a continuous, mainly continuous beam that allows to run coincidence experiment, and the beam is delivered to 4 different experimental holes that can run in parallel with also different current, different energies up to a certain possibility of changing the energy, but roughly speaking, we can run at low and high energy at the same time. And so experiment that require a long time or short time can run in parallel. And together with that, we have a beam that is fully polarized. Not only the beam, but also there is a solid program, physics program that include the polarized target and many different flavor of polarized target, nuclear target that allows to explore also the spin degree of freedom of the scatter. Just to give you a sense, luminosity we reach routinely is in the range of 10 millions to 100 millions times the luminosity originally used at SLAC for the first DIS measurement. So it's a kind of a new measurements, is a new physics program based on let's say old physics, but done in a very modern way. And in particular, one of the key tool to run the program is the detector. The detector is so-called the CLAS12, is the detector that is replacing the old one that was the CLAS, the CBAF larger acceptance spectrometer, now running at 12 GeV. Is made by 2 different parts, the forward detector and the central detector, with the forward detector based on the torus magnetic field up to 1.5 Tesla, instrumented with and Cherenkov counter for the electron identification, drift chambers for tracking, and also the electromagnetic calorimeter again for the electron and neutron particle identification, plus a time-of-flight system for particle ID. Central detector is based around a solenoid magnet up to 5 Tesla. This is mainly meant to shrink the Muller electron produced in the primary beam with the target, shrink them and focus them within the beam line. But together with that is also instrumented with the barrel silicon tracker and central time of flight in order to measure the hadron produce a large angle, for angle that goes larger than 45 degrees and then cover mainly the backward hemisphere of the scattering. Together with that also we had an upgrades of the baseline detectors that include the micromegas, barrel and forward, neutron detector, in particular for the forward part, also a rich detector that is meant to measure separate kaon and pions at very large momentum transfer up to 8 GeV. So this gives you a unique capability to class 12 to do semi-inclusive in a region where it's quite difficult, in particular for flavor separation. And then another system that instruments very small angles around the beam line from few degrees, 2.5 up to 5 degrees, the so-called forward tagger that allows to run mainly quasi-real photons, or if you like, a very low Q-square electron production in a very similar way as Zeus did many years ago, or CERN or any high energy facilities producing real photon or quasi-real photon. We are talking about a virtual photons in the range of 10 to the -2, -3. So it's they can be considered for any practical effect like real photons. This gives also the capability of running part of the program that is very similar to what the GlueX in whole B is doing. What I'm showing here is that class 12 is not only a CAD drawing, but this is a real detector that is fully operational and is already working for a couple of years, collecting data. All details were reported in a recent publication that we produced last year. There is an overview paper that describes the characteristics of the detector together with the dedicated, there are 17 of them, 17 dedicated papers describing in details the behavior and performance of each of the sub-detectors, since the spectrometer is based on many different components and each of them deserve to be described in full details in particular. Just to give you a sense of the kinematics covered by the detector, here is the Q-square versus X, or if you prefer Q-square versus W, covered by a standard run at 10.6 GeV with a standard torus current. Obviously, you can change a little bit the configuration, in particular changing the torus polarity. You can access large angle electrons rather than standard that goes to the different combination of the different angles covered by electrons going towards the beam line or in the opposite direction. In this case, this is for what we call in-banding, for the electron going in-banding. And this is shows that the most part of statistics is accumulated in the region of the valence quark between 0.2, let's say, up to mainly 0.8. That is the region that we can better cover with the detector, with a quite significant significant span in Q-square. You see that we can easily cover up to, let's say, 8 with a sizable statistic. That doesn't mean that we cannot go higher in both or lower in X or higher in Q-square, but clearly we are going to pay a price for the limited statistics and acceptance of the detector. This plot is just based on 200 minutes of data taking, so you can imagine we are talking about taking data for years and not days. So you can easily imagine how rich and how complete is the kinematic coverage given by class 12. The whole B physics program is quite complete in terms of hadron physics, both including interaction of nucleons, studying in particular the evolution of quark hadronization and nuclear transparencies of hadrons in nuclei, but also the 3D structure of the nucleon, in particular for 4 factors, PDFs. The 2 main items are GPDs and TMDs, but there are also other side items, like for instance, quark confinement, role of the glue in the meson and baryon spectroscopy. This is part of the program, but also some physics beyond the standard model. But I'm not going to talk about that. I'm mainly focusing on class 12. And class 12, since even the standard, let's say, hadronic physics program that we are going to cover with class 12 is very rich. The way how the different proposal and the different experiments are organized are reported on the left side of the slide, where you can see the different so-called run groups that are a collection of experiments with similar experimental conditions, can run mainly together. And in this way, the total sum of days that account for 3,000 mainly experimental days can be reduced to about 1,000. Still, you can imagine given an efficiency factor of 2, still correspond to about 10 years maybe of full physics program, already scheduled, already on the book, ready to go. The different run groups are according to the different combination. We start from the standard liquid hydrogen target, mainly focused on the 3D structure, function, and meson X. So the meson and baryon spectroscopy, to more fancy and more sophisticated experiment that require polarized target, like for instance RGC that require longitudinal target, but we have a strong program also with the transverse polarized target, and low energy, for instance, recoil with bonus that is on deuteron target, but gaseous, plus an RTPC to measure the recoiling proton, or even projecting on the future experiment on helium-3 polarized target is with a brand new technology that we are studying and possibly importing also within the class 12. And together with that, there are also in the whole other experiment like HPS looking for the dark sector, exploring the dark sector, or PIRAD, that this is a dedicated experiment to measure the proton radius. But I'm going to stick on the class 12 name. So now, if we look at the particular the GPDs and the TMDs program, that is the one that I think is more relevant for this conference and this venue. If we look at the clearly Q-square allows us to look at the nucleon at different scale, and looking at the distances that are bigger than a single 1 Fermi, you see the nucleon as an entire object. And going down in your resolution power, you start to see the 3 valence quark and the interaction that they have, and obviously increasing then your capability of going down, you will see gluons in action and interaction of partons rather than constituent quarks. This is traditionally studied by elastic scattering and deep inelastic scattering. If you want, there are 2 extremes to extract for elastic form factors in one case and PDFs in the other case. Now, nowadays, new technology based on exclusive scattering allows to in some way combine this information, what we call the generalized parton distributions, and even more than that, you can really find a general description of the different processes, starting from the Wigner function that depending on which variables you integrate over, you end up with the TMDs or the GPDs in 3 dimensions in the full kinematical space, where all variables are considered, in particular to extract information about the transverse plane that usually is not measured. This is clearly very demanding in terms of experiment, because this is a multi-dimensional space that require binning your data in different variables. If you don't want to lose part of the information, just integrating over the variables, and actually what we are expecting is that the correlation between quarks can only be revealed if you don't integrate over the different environments. So this is calling for experiment that needs to only modern experiment can access the full information embedded in TMDs and GPDs. So high luminosity, polarized beams and target, and obviously sophisticated detector systems are kind of requirement for this program. It is exactly what we can do with CLAS12 at Jefferson Lab. I'm gonna just briefly report about the first two measurements that we got so far, submitted to PRL. One of them accepted, so ready to be published, and the other is under review, but obviously the program is much more rich than what I'm presenting. This is just a few words about the CDIS, so the semi-inclusive deep inelastic scattering. In this case, the idea is that you have a PDF embedding the information of quark correlation within the nucleon.
Marco, we have lost. Oh, you're back. Thanks.
Excuse me?
For a moment, audio was off. Please continue. Sorry for interrupting.
Sorry. No problem. Okay. So the virtual photon then interacted with one of the quark and produce a hadron and another function describe the hadronization of the quark in the final state. So together with that, depending on the different combination of polarization of nucleon and quark, you may access to different structure functions that describe the interaction. This is a way to move forward from the typical longitudinal structure function described by 90% of the study performed so far, and move forward and try to see correlations, particular transverse in the transverse space correlation. Together with the TMDs, the other important experimental assessment of the nucleon structure is based on exclusive reaction. It is a little bit more complicated from the experimental point of view, because in this case you are really looking for a closed kinematics where you measure a final state, exclusive final state. And here the idea is that having the quark, the struck quark forced to re-enter in the nucleon and stay in an intact nucleon in the final state, in some ways providing new information, providing specific information about the GPDs and a set of structure function only accessible in this way. Leading
5 more minutes.
Yes, leading experiment for that are the DVCS and TCS that are in particular when a photon or a virtual photon is produced. In this case, you have the possibility of measuring both the imaginary or the real part of the process, and then again gaining information about different combination of GPDs function. Again, just to give you an idea, here is how on hydrogen, how the nucleon looks different when you run at 2, 6, or 10 GeV. You see, obviously, the physics that is revealed is completely different from the elastic scattering to the baryon nucleon excitation up to the deep inelastic scattering at large energy. Again, so this is just for lipid hydrogen target. You see there is a long list of experiments. Each of them focus on specific part that cover the TMDs and GMDs program, but also fracture function for factors, or spectroscopy in particular for baryon and meson, nuclear resonance, strange baryons. This is really a rich program that is possible given the high rate and the big capability of the detector of collecting data all together with a very loose trigger. We are collecting actually data at 12 kilohertz rate with about 500 megabytes per second with a very high lifetime, and with just the electron detected that allows them to offline to select the interesting kinematics or the interesting reaction. Data were collected. Now it's about 2 years that CLAS12 is operational, and over that, about 3/4 of the accumulated statistics is ready for physics analysis. Just again, just to give you a flavor of what we have over the very rich program that we are exploring, these are only the couple of papers that were submitted and accepted actually this year. One of them is about the single pion type class production and the CDs physics. Again, the different combination of multi-dimension analysis in X, Z, PT requires a full measurements in the entire phase space. So far, we just focus on asymmetries, but for the future, we are planning to measure cross-section. And on the left side, you can see here Q² versus X as being reported by the measurements, or Z versus PT, and how the data are covering almost the entire phase space. On the right side, there is just projection in 1D as a function of X, Z, and P of the, in this case, this is the F, is the asymmetry as a function of sin phi. And you can see that this is compared with the previous measurements and the quality, the error bars of tiny that are within the markers, and also the kinematic range covered both in 3 variables is quite impressive. And obviously, based on that, the models allows to extract, in this specific case, Collins and TMD twist 3 components and disentangle the combination, the convolution, complicated convolution present in the symmetry. This is the idea. This is just a single 1D extraction, but obviously the final aim is to really look at the asymmetry or even the cross-section in the full multi-dimension phase space and extract the information directly from that. Same thing for a even more complicated kinematics for the dihadron. This is a kind of brand new frontier for the semi-inclusive deep inelastic scattering, because in this case there are only very few information available. Here you can also have not only the standard fragmentation function, but the dihadron fragmentation function, something brand new, never measured. And again, you can see here the asymmetry as a function of X-Bjorkin, of the dihadron mass, the change of sign when the dihadrons move from below or larger than the mass of the rho, and how the asymmetry looks like for the 2 kinematic regions, red and
Marco, the 20 minutes are over. Just
yes, I'm almost done. Just another couple of slides.
Thank you.
This is obviously what I presented as being submitted and well, let's say understood. We are also working on presenting the same thing for more complicated final state, in particular exclusive reaction like the DVCS from low energy, from high energy, from proton and neutron. And again, these are quite brand new results. And just to conclude, a few words about what we are planning to do this year. Well, this will be dedicated run from October to December with nuclei for first time in CLAS12. There will obviously another very interesting sector, not only for short range correlation, but also the PDF part directly of nucleon within the nuclei. Just my final conclusion. So we have a comprehensive hadron physics program that just started with CLAS12 at Jefferson Lab. Nucleon structure, GPDs, TMDs, light work, mesospectroscopy, and other nucleon structure are all the different items that can be studied with CLAS12. We have a rich and long physics program, about 10 years from now on, that make a good use of high intensity electron beam, and also significant coverage. That is in some sense a playground for the future for the electron ion collider. This will be necessary studies that will complement the kinematics reached by the EIC. So CLAS12 just started producing results, and we are now ready for publication, and many more are coming in the next future. Thank you very much for your attention.
Thank you very much, Marco, for your really excellent overview about the CLAS12 experiment at Jefferson Lab. We have about 3 minutes left for questions to Marco. Are there questions? JP, please.
Yes, just a quick question. With class 12 results roll in, are your analysis speed can keep up with the speed data coming in, especially from long-term, how the software analysis processing and result come out can keep up with it?
Thank you for the question. Yes, we are putting a lot of attention. Obviously, we are moving from, let's say, the phase where we just started to try to understand how to efficiently collect data, but also process data, because as you correctly mentioned, it's not only about running the experiment. In particular for class, we know, I mean, these 4-pi detectors are collecting data, a huge amount of data, then required to be calibrated, that are required to be in some way what we call the cooking phase, and then finally available for physics analysis. This clearly require time, and what we are trying to do now is to move the part that is more demanding in terms of time is not really, as one can think about, is not really the CPU time necessary to cook data. In some way, this is automatically done by a farm of CPUs available at Jefferson Lab. The really longer part is about the calibration and be sure that the quality of data, I mean, it's all the control that are necessary to produce high quality data. And what we are trying to do, and this will start from the new data set we are collecting this year, is try to do calibration in real time, or let's say semi-real time. More or less having at the same time we are collecting data, also selecting some golden runs that will be used for calibration, and then try to run at the same time. This gives us not only, you know, a more efficient procedure, but also having the full knowledge of the experiment running while you calibrate your data, so you know exactly what's going on. This is the idea. So far, we started with, let's say, 2 years backlog. So we started to cook data that were collected 2 years ago. In the very last run that happened in last summer, we are now in a 6 month. I mean, we are able to produce results to get, let's say, data for physics analysis, high level analysis in 6 months from when we took data. Our aim is to reduce, you know, just a couple of months after that we take data, ready to go, ready to be analyzed by the different analysis group.
So Paul also had his hand up. Do you have a short question? Please go ahead.
Okay, so Marco, thank you very much. Really great talk. I've been staring at slide 11 and trying to understand the sort of relationship between the observables and TMDs and so on. And I just wondered, are there already studies that sort of show the sensitivity to TMDs and GPDs directly from the observables that you plan to measure?
Again, in truth, this is it's a really tricky question, because it's clearly this is a multi-dimension problem. And as we learn, in particular from spectroscopy, where you have to deal with many particles in the final state that necessarily involve many different degree of freedom, the information is really embedded in correlations. So you really have to have not only, you know, the measurement itself, you have to have a very sound framework where you extract, how to extract this information. And in particular for the TMDs and the GPD program is exactly the same. You have a 5 or 6 dimension space where the information is not ready or available directly. So you really need to work in parallel together with the experimental program that collect the data with many different channels in many different kinematics. You really have to have a sound framework to extract this information. This is exactly what, in particular, the theory group at JLab is working together with experimentalists in order to provide all the necessary, not really theoretical, more, let's say, phenomenological tool in order to extract this information. And obviously, it's a combination, as we had, for instance, for the first publication. Asymmetries are even more convoluted quantities because they contain the PDFs, Collins or Mulders, in particular for for the single pion production, but they are convoluted also with the unpolarized function PDFs, and also twist tree and other parts that are necessary embedded in them. And then what we did was just try with different models, but this is too naive. It's clearly to really exploit the information that is contained in this measurement. It's really necessary to do a multi-parametric, let's say multi-variables in this multi-dimensional space extraction of this information. This is a work in progress. I think that there is among the theory community, there are different proposals, different way. There are practicalities that complicate life. I mean, it's not only having clear in mind what you want to obtain, but it's also the way how you are doing that. I just want to mention that there is a strong support from the theory group that is working with us, with the experimentalists, in order to fit. I mean, I think that the main problem here is that each measurement.
We need to move on to the next talk. I really would like to thank you for this very interesting start into our session, but we are clearly over time now. But this was a really interesting discussion. Thank you very much. We stay at Jefferson Lab with the next talk, and JP Chen will give us an overview about a future experiment which is planned at Jefferson Lab, which is solid. And I also will give you a 5 minutes warning. And so after 15 minutes. Thank you very much.
Okay, yeah. First, thanks organizer for the invitation. Yeah, I would like to tell you more physics program from Jefferson Lab, a planned future project detector called SOLID. I need to thank all our collaborators, especially Hai-Yi Gao, Zeni Mezeni, and Paul Sauder for help with some of the slides. I will, with a brief introduction, and then I will go on with the three main physics programs: parity violation DIS and semi-inclusive DIS, which is mostly to study TMDs, and also the GSI threshold GSI production program. This is to probe the strong gluon field and relate to proton mass. And we also have, these are the three main programs, and we have quite a number of run group experiments runs together with these three main programs. And then near the end, I will give a brief introduction of the layout, device, and the status of the detectors. Then I will summarize. Okay, for the introduction, you probably already heard that JLab from 6 to JLab 12, it's compared with all the other electron lepton scattering facilities, it has the highest luminosities. But if you look more closely, if you not just also with acceptance weighted for parity violation DIS type of experiment, you will see SOLID is the new proposed ones can have large acceptance and handle luminosity up to 1039. So it's orders magnitude more than how AC and the class 12 can do. Okay, the main goal and purpose when we start with the SOLID proposal to upgrade, the main thing is most of the JLab experiment in Hall A, B, C, and D is either you have large acceptance or you have high luminosities. But what we know, JLab can electron beam can deliver luminosity correspond to luminosity up to 1039. But most of the large acceptance detectors, such as class 12, can handle only 1035. So that's where we thought we need to fully take the advantage of JLab 12 GeV. So we want to design a detector which can take can take up to 39, but that's with some buffer. Without buffer, it can still take 1037. So this will really allow us to take the full potential of JLab 12 GeV. So there are three main pillars of the physics program. One is to push the phase space to search for new physics, use separative evaluation, DIS, and do the 3D momentum imaging, which are the TMDs related to nuclear spin. And also it has a very nice sensitivity in the threshold region, things with JLab 12 GeV with class threshold for GSI productions. Where these GSI heavy quark productions, you can learn some of the important physics related to proton mass. So this is really complementary and synergistic to the EIC physics. So I start with the first part is the PVDIS. It's try to test standard model. Also, it provides some precision study of hadronic structures. So with parity evaluation, you actually take advantage of the interference between the photon exchange and the Z0 exchange. So the asymmetry in this case will be basically your Z cross sections divided by your photon cross sections, because they squared the square term cancels. It's only the interference term stays. In the simplest case, we choose like deuteron, the isoscalar nucleus. Even structure part are mostly canceled in the leading order. So it's very sensitive to the electroweak structures. So in this case, it's only the C quark in the radial collection part that come in. So you can see the symmetry are sensitive to the coupling constant. We call it C1s, and the C2s due to U and D. It's electron and quark couplings. And I will show you in the later part how we combine with the raw data to get this kind of coupling constant. In the large X region, all these R's due to the C quarks will basically cancels or goes to 1. Okay, the experiment takes the advantage of really high luminosity, 10 to the 9. So we try to do is cover a very wide range. In every single beam, you measure this parity evaluation asymmetry to be below 1%, 7%. So with this wide range, in the middle range, you can high Q square part, you can do a clean beyond standard model search. At highest X, you can looking for interesting physics, hadronic physics effect, like charge symmetry evaluations. And then each X range, you have some Q square range to help you study the high twist effect. In this case, actually, twist 2 cancers, you can sensitive directly to very interesting spatial high twist 4 effect. The left plot, there's a zoom in version. The blue is the very first parity evaluation experiment, which from SLAC in the 70s, which really helped to establish the standard model. It's one of the probably the most significant electron scattering experiment. You can see 6 GeV with the first testing type of run with parity evaluation. That's the light blue, which you can see significantly improved by effect of almost order of magnitude improvement over the SLAC experiment. Now, what we're going to do with solid will be another order of magnitude improvement. That's the middle, the small elliptical. And combined with the Q weak and other experiment, which may have C1, DIS parity evaluation sensitive to the combination of C1, C2, while elastic is only sensitive to C1. So combined with this, you get both C1 and C2 out. The right side is showing the sensitivity to new physics in energy scale. In this case, the larger the better. you can see the with published data, you get this red in the center, and with planned P2 experiment at mines, you will expand in the horizontal side, and then in PVDIS, you will expand the vertical as well as the horizontals. So you were sensitive to physics at the energy level of 20 to 30 TeV scale. I don't have time to show you all the other physics, like it's sensitive to leptophobic Z prime, dark boson, Z dark. And also it provides a precision study of charge symmetry variations I mentioned, high twist effect. Also, if you do not on deuterium, but also on proton, which is also planned, you will have a very unique sensitivity to D over U without any nuclear physics effect. Just on proton, you get a different flavor combinations. Okay, the second program is semi-inclusive DIS. This will give us the transversely tensor charge and other TMDs. I show you there's the previous speaker already mentioned there's 8 TMDs in the leading twist. I'm showing with the transverse polarized target, you can access 3 of them. And actually, in principle, we have longitudinal polarized target, we have unpolarized together. You can access all 8 of them. But I just show these 3 as examples. Actually, even in my talk, will be focused on 2, transversity and Sivers. Transversity itself also can be integrated over, will give you it's a collinear quantity, and even integrate over X give you the tensor charge. That's we'll talk about this. And the Sivers give you the correlations of nuclear spin with the quark orbital angular momentum. So that's a very unique correlations. And the periodicity give you the actually like quadrupole type 2 unit of orbital angular momentum come in. To separate this experimentally, semi-inclusive DIS is the best, cleanest way, similar to also JEM is also clean. So your asymmetry with transverse polarized target, unpolarized beam, you will have in the leading twist, you have 3 terms survive, which is Collins and periodicity and Sivers. And they have different angular modulations. So by use the angular separation, you can separate all these 3 together separately. And each one will be sensitive to a combination of, it's a convolution of like Collins will be the transversity converted with Collins fragmentation functions, which you can get from E plus E minus, or you can also, with enough observer, you can also have a contribution from study from semi-inclusive DIS. This is just show you, we did experiment the 6 GeV. That's the black data point on this plot. And that's not a dedicated one, it's just demonstrate you can do it reasonably well, and we train the students and all that. With solid will be much better. Each Q square Z being, you have different PT and X, these 4 different dimensions. We have over 1,400 beings, and each one will be at order of, you can see the error bars is order of magnitude better than our 6 GeV data. So this really provides very high precision 4-dimensional binning of the Collins asymmetries and the Sivers as well. So we have 3 experiments approved by PSC with the highest rating A with solid, and 2 are used polarized heme 3 to study neutron, longitudinal, and transverse polarized. And 1 is used transversely polarized protons, use NH3 target. So this are the 3 main programs for CIDUS. These are the impact study. We work with our theorists together to see where's their model to see the impact, how the word analysis shows the uncertainties for transversely for Sivers, for U-quark, D-quark, and then look at if you add solid data in how this will change. And the improvement, if you look at the error bars, reduction is at, like for D-quark is really order of magnitude, a factor of 10, or in Sivers can be up to a factor of 30 improvement. So with this, we can get very precise tensor charge, the projection of tensor charge. These black things are all the different world analysis use the model for existing world data. You can see that with solid it will be significantly improved. And this has a very nice lattice calculation already exists with high precision small error bars. So this will really provide a very nice benchmark test of lattice calculations. And this also provide input when you use for EDMs, this tensor charge as a coefficient there. So this help study new physics with the EDM search. The other one is for the Sivers functions. This really study the confined motions and nucleon. And again, the improvement are significant. And I also want to show you one thing is to study the intrinsic motion, the transverse momentum. And the current, that's of course, you need a model to help you do that. And the current uncertainty, knowing the transverse momentum average U and D quark, and with solid, you will be improved by more than the order of magnitude. So that's really shows the power of solid precision data. Okay,
you have 5 more minutes, JP.
Okay, I go to the last pillar of the physics. It's a GSI experiment. And GSI will provide information, help you in understand the proton mass, and in a way which use Shandongji's way of separate this. You can see the Hamiltonian, which relate to energy, can be separated into the quark energy, quark mass, and ground energy, and then the quantum anomalous energy. That's the part which you will know very little, and others you can get from other various different sources. So to understand, to learn about this quark anomalous energy, they used to call the trace anomaly, and how to get this is the discussion recently been heated up. And so from measurement in the threshold heavy quark cross sections, you can lead to the trace anomaly, and you use approximations, vector meson dominance. The real part really directly relate to the trace anomalies. Okay, there's a lot of theoretical studies. So this experiment will measure both photon productions and electron productions, and with high precisions. So these are show the precisions. Like currently use GLUX data. These are the limits come from these red lines, but will be shrink down to very, very precise with these blues. And these are the data we can take with different triggers, electron production and photon productions. And not only we get proton, we can also the proton mass, but also we'll learn more about the anti-quark. The HCB found this. Okay, this will be complementary to what ERC can do with the beauty. So remaining time, I just want to go through very quickly the other program we're still developing. One is the GPDs. So they are direct review recommend with such a nice high luminosity detectors. They suggest us also looking into GPDs. So this is being looked into. We'll get 2 experiments run group approved. One is the deep exclusive pi minus production use transverse polarized helium-3 target. That's never been done before. So this will be a first to contribute very uniquely to the GPD program. The other TCS experiment. Also, we're developing, which is most luminous in Hungary, is a double DVCS, DDVCS. So this have a letter of intent, get endorsement, but still need some work to develop into a full proposal. The other is DVCS on polarized proton and polarized heme3 target. That's also under development. And in addition to the GPD, there's a few other approved run group, like dihedron, which also mentioned in the previous talk. And we also have chaos, and also single inclusive out of plane asymmetry, and inclusive DRS experiment G2, D2. Okay, I just very quickly show you what are the detectors. So that it's very demanding, but start from beginning, we use more modern technologies allow us to be able to get to higher, deal with high luminosity, high data rates. So we use GEMS instead of GF chamber. We use Sheshik, EKL, use pipeline DAQ, also very fast advancing computing capability really helped us. And the Chen curves, we use high performance Chen curve and use some buffer to help for the PVDIS. There are two different configurations, one for Sivers GSI configuration, one for PVDIS. So detectors for PVDIS only detect electrons. It's just one additional buffer, but use Cherenkov and EKL for particle ID and then the GEMS for tracking. For Sivers GSI, we have more. In addition to GEMS, we have large angle EKL sintered pattern detector, and also for the angle, you have heavy gas Cherenkov and MIPC for hadron particle ID. Okay, so that's just want to tell you we have this large acceptance detector which can handle very high luminosity. That's the solid detector. This way push the limit of the intensity frontier. This program has a very rich and violent science programs complementary to the proposed EIC, also complement to some other world JLab experiment. So we've been developing this for a decade. So we already have a quite mature pre-conceptual design report. And just last month, so we finished the DOE science review. We have a very strong collaborations, but we still like to welcome new collaborators if anybody is interested. There's more information on the website. Thank you, that's it.
Thank you very much for introducing the solid experiment and really showing the capabilities of this experiment, as you mentioned, complementary to the EIC. We have time for 1 or 2 questions. I don't see any questions up, so let me ask a short one before we then go to the next talk. What do you think are the challenges in realizing the solid experiment?
First, of course, we need to get the DOE give us the funding. It's quite costly. That's what the first step is get the science review. So that's necessary to get CD0. Yeah, DOE has been kind of with other things going on. So they postponed our science review until now. Finally, they're ready to move forward with that. So we just did the science review. And then in terms of technical part, physics-wise, it's very rich. There are many young people, postdocs, young physicists keep developing new physics with that. It's general purpose spectrometer detectors. But in terms of technical, every single detector is kind of challenge. We really pushed them all to the limit. But we also keep an eye on all the new development. So keep option open whenever we have some headroom in meet our challenge requirement. But also whenever there's a new ones, like for GEM, we just switch to use all the readout system to the new ones. We're doing, DOE gave us some money to do the pre-R&D to demonstrate this. Not only it meets, it will significantly improve the performance. And whatever we proposed, probably by the time we build, it should exceed the expectations. The computing part and the DAQ is also very challenging. And that's also the other part to do. You give us money to do pre-R&Ds. So these are, of course, as the question I asked for the previous talk, is once we have huge amount of data come in, we also try to make sure we can deal with this, be able to processing, not just the computing itself, but also the be able to do the prop calibrations, processing to get to the all the technical information and the physics information out.
Thank you very much. So we heard about already spin physics at Jefferson Lab with CLAS12 and with the planned solid experiment. And now we hear about an interesting proposal of doing spin physics at CERN. Marco Santimaria will present us about the LHCspin project.
Yeah. Hello, everyone.
Sorry, I need
yeah, to unshare, please. Yes, thank you.
Yeah, right. Yeah.
Can you see my slides?
Yes, and I also will give you a 5 minutes warning.
Okay, thank you. So, hello everyone. I'll give you a quick overview of the LHCspin project on behalf of my colleagues. So let me start with LHCb, since this is where the detector where the setup will be located. So this is the general purpose forward spectrometer, which is fully instrumented in the pseudo-rapidity region from 2 to 5, and actually optimized for the detection of C and B hadrons. So I won't go into all the details of the detector. You can have a look at Diego's talk for this. I just want to mention that we have excellent particle identification capabilities, which we do with the 2 Cherenkov detectors, reach 1, reach 2, and then the calorimeters and a series of muon stations, which are these ones in green. Thanks to our tracking system, which starts from the vertex locator here, and a series of tracking stations, 2 before the magnet and 3 after, we have an excellent momentum resolution, which is below 1% over the full momentum spectrum. So for the run 3, starting from next year, we did a major hardware intervention, essentially, to our detector. And we also installed a non-polarized gas cell, which you can see here, just attached to the Velo. So these ones you see here in the picture are the Velo detector boxes, and this one is the SMOC2 cell. So this, in principle, can be filled with a lot of different gases, I've listed here, with a negligible impact on the beam lifetime. So the SMOC2 will boost the LCB fixed target program, which is active actually since 2015 for the run 3. So since starting next year. This also sets the basis for the development of a polarized gas target, PGT, that we want to install during long shutdown 3. So this is the aim of the LHCspin project, to start taking data from run 4. And you can have a look at this link for more information. So we already have an excellent starting point with SMOC2, because we developed a trigger for taking data simultaneously for proton-proton collisions and proton-gas collisions. This is proved to have a minor throughput impact. So the results we use for the LHCb real-time event reconstruction are very minor for the SMOC2. And this will make LHCb the only experiment able to run in collider mode and in fixed target mode simultaneously. You can see here on the plot on the right side that for the beam target region, so this is the Z coordinate of the vertex, the beam target region is upstream with respect to the nominal PP, and we got full tracking efficiency also in this region. So before I move on, let me just give you some numbers on the kinematics. We have 1 fixed target collisions. So we got proton-proton on proton gas with a 70 eV beam. We got the center of mass energy of 115 GeV, while for the ion collisions with other hydrogen or heavier gases, we got 2.76 TeV beam in case of lead, and this makes a square root of S of 72 GeV. The products, however, are largely boosted because of the very high energy of the beam. This gives us access to the very large X2 value, so the negative X Feynman region. So this will bring the unpolarized physics, and for the first time at LHC, polarized physics, and exploiting one of the most advanced we're able to do this with unique observables by accessing the large X content of gluons, of anti-quarks and heavy quarks in both nucleons and nuclei, and to probe the spin distributions of the gluons inside unpolarized and polarized nucleons. Whereas concerning the heavy ion fixed target collisions, those will be an energy which is in between the one accessed, reached at SPS and RIC. We also have unique features. The first one is a very broad and unexplored kinematic range. You can see here in orange in this plot. And we're able to do this with a very high luminosity, exploring the luminosity of LHC, and with the high resolution and reconstruction capabilities of the LHCb sound detectors. We can do this with proton and heavy ion beams, which are usually scheduled at LHC, with a large variety of gas targets, and with LHC spin project with polarized hydrogen and deuterium. So I'll now show quickly a selection of physics cases from LHC spin. Let me start with the PDFs. So this is, generally speaking, a very interesting point to reduce the uncertainty on the PDFs, as in the example, the gluon PDFs in the large X region. This is an essential ingredient in general for the high energy physics computation, and also an important input for FCC measurements. By doing measurement on the heavy flavor hydro production, which is very suitable at LHCb, we can improve the knowledge of the prompt neutrino flux. As you can see from this plot here, there is quite a sizable uncertainty coming from the PDFs. You can also do search on the intrinsic chunk component, so I won't go into the details, just have a look at Tom's talk later today on this measurement. Another interesting measurement we can do on proton helium is anti-proton production, which allows a better interpretation of the dark matter annihilation. And also many more examples. I don't have time to cover here, just want to briefly mention the improved knowledge on the flux composition of ultra-high energy cosmic rays, this with proton, helium, oxygen, and nitrogen collisions. To get more insight on the MC effect and nuclear PDFs in general, and also the possibility currently foreseen for the run 3 to run at LHC a beam of oxygen. So physics case number 2 concerns the deeper hadronic structure, with ultimate goal here to reconstruct to do a 3D tomography of the hadrons, as shown in this picture here. This can be done by accessing quark TMDs with single transient spin asymmetries in the high X region. So the basic observable will be this one. We've seen this many times, and this gives access to a series of TMDs as listed here. This two plot here below, I show the projected precision for polarized Brownian and heavy quark probes on these kind of observables, and you can also appreciate here on the bottom right what is the Feynman X region we access compared to the one by Phoenix. The heavy flavors at LHC are mainly producing gluon-gluon collision, and LHCb has a very high capability to reconstruct a large sample of quarkonia states with very high resolution. So this means very narrow invariant mass peaks. So we can do this with a lot of probes, from the ETA to the Chi-C, J-Psi, and also open heavy flavor like D and B mesons and so forth. So these, many of these probes are fully accessible from other hadronic experiments. So this will be very interesting. As a last item, let me say also we'll be able to probe the GPDs with the ultra-peripheral collisions. This can either be done with the deeply virtual Compton scattering or with the exclusive J-psi production, the latter being sensitive to the gluon GPDs and eventually linked to the gluon orbital angular momentum, for example, with the G-sample. And here below is an example of a 3D picture that can be built with the, this comes from Hermes results in the impact parameter space. So last physics case concerns heavy ions. In this case, on the quark-gluon plasma, we will complement the RIC beam energy scan in the transition region by doing a rapidity scan. And so this is the transition region between bound hadrons and free quarks and gluons. We can also construct a thermometer by observing the sequential suppression of CC bar bound states, as shown here in this picture, since this means that these resonances have different binding energy and thus different dissociation temperatures. So as a last item, I want to mention something that joins heavy ions and polarized target, which is ultra-relativistic collisions of heavy nuclei on transversely polarized deuterons, is to probe the dynamics of small system. As you can see in this picture here, the deformation of the polarized deuteron here in red is reflected in the orientation of the fireball, which is created out of the collision with the heavy nuclei, which is here. So this is quantified by the electricity as shown in this plot. So a few words on the setup. This you see here is the basic setup from Hermes, which is our starting point. So of course there is the target cell here, the LHC beam coming this way. And then the injection of the polarized atoms from the atomic beam source, or ABS. And then on this other branch here, the analysis phase. So that is made up of a target gas analyzer, or TGA, to measure the atomic and molecular fractions, and BRP, so bipolar polarimeter to measure the nuclear polarization.
You have 5 more minutes, Marco.
Okay, thanks. So this will be our starting point. Is the picture from the Hermes setup, but we'll need to do a step forward, as you will see in the last slides. So this is a few sketches on the developments we're doing on the cell and the magnet. So the cell will occupy the same region now used by SMOG2. SMOG2 has a size of 30 centimeter in length and 1 centimeter in diameter, and the LHCspin will occupy a slightly larger volume. This is shown here on the bottom. This in green is the Velo vessel, and this is where the setup will be located. So as I mentioned, this will allow to both inject polarized and unpolarized gas. And on the right side, you can see some developments on this compact superconductive dipole magnet we are developing just on top of the cell. This will provide a static transverse field, so on this direction, with an intensity of 0.3 Tesla, the possibility to invert the polarity, of course, and then an homogeneity of around 10%, which we found suitable for the LHC environment. Concerning the ABS and BRP, so this will need a step forward, so because we need to reduce the size with respect to the previous sketch shown from Hermes of both these two items to fit into the available space we have in the LHCb cavern. So an example is shown here on the left side. The injected intensity of hydrogen atoms we aimed at is the current working point was used at, that was reached at Hermes, which is 6.5 × 10⁻16 atoms per second, while the luminosity in the high luminosity LHC phase at LHCb would be around 8 × 10⁻32, so very high. Right, concluding in this timeline, I just summarized the fixed target program of LHCb. So SMOG1 starting from 2015, and then SMOG2 to take data with the LHCb detector from next year, and then the LHCspin for run 4. So in general, the fixed target program is very active and now greatly boosted with the SMOG2 cell. With LHCspin, we want to bring this to a step forward and achieve for the first time spin physics at the LHC, exploiting the LHCb detector, which is well suitable for this purpose. I've shown you that the R&D calls for a new generation of polarized gas targets. So this is undoubtedly challenging, but very worth the effort. So I show you a very rich physics program with new probes and a program which is complementary to both the existing facilities and the future capabilities of EIC. Thank you.
Thank you very much for this great overview. And I'm very happy to see, as a Hermes coloration member, the Hermes target, then in a certain context. Are there questions to Marco? I don't see any raised hands. Klaus?
Yeah, I'm a Zoom host, so I cannot raise my hand. I'm sorry. Marco, I have maybe a stupid question. If I understand correctly from your slide number 4, you are running simultaneously collider and fixed target. That means you have the fixed target in the collider, so you can record both at the same time.
Yes.
How much or how many times does it happen that a fixed target event will overlap with a collider event?
Yeah, that is a good question. So we investigated this into details and found that the overlap is very small. This is due to the fact that being gas collisions are at much lower occupancy with respect to the main PP collisions, and the handle we have on this to separate is shown in this plot, which is the PV-Z coordinate. So our resolution we had on the Z coordinate of the primary vertex allow us to detach the two topologies. So the overlap is completely negligible.
Okay, great. Thanks. Very interesting. Thank you very much.
I have a short question for you. What is the critical path to realize LHCb is spin?
Yeah, good point. I would say that the hardest part is to build compact ABS and BRP. So I'm not expert of these two techniques, but I think that reduce the size of these two items will be challenging. So I would say briefly that the hardest challenge would be to make this setup compact.
Thank you very much. And also thank you for pointing out the complementarity to what EIC will measure. We will now hear contribution from EIC. EIC puts a lot of emphasis on forward physics, and Wan Chang will present investigations of coherent production background and EA collision geometry using forward particles at the EIC. And great talk, Marco. I really enjoyed it.
Thank you.
Can you see my screen?
We see your screen. We see your summary slide, and we not yet see it in full screen.
Oh, I'm sorry.
Are we getting there?
Oh, okay. Wait.
Okay, now we have the first slide. So we are excited about your presentation about forward physics at the EIC, and I will also give you a 5-minute warning.
Okay. Thank you, everyone. Today I'm going to give the presentation about the investigation of the coherent JPSI production background at the EIC. That is to wait with the incoherent event. At EIC, one of the most important measurements is to obtain the gluon density distributions in the heavy nucleus through the measurement of a coherent JPSI production. However, the background from incoherent process could be overwhelming, swaps the coherent production. As this plot is the equal differential distribution with respect to T for JPSI production for the coherent and incoherent events. The T here is the momentum transfer between the incoming and the outgoing nuclei. The square represents the coherent events, and the circles are the incoherent events. The differential cross-section can be directly related to the transverse spatial distribution of gluons through the formula transformation. But a challenging issue is that for the high value of T, the incoherent production overtakes the coherent production. So we need to be able to wait to the incoherent case in order to measure the coherent events. In my analysis, we use the BEAGLE event generator to simulate the E-light incoherent diffractive gypside production. In order to surprise the incoherent process, the final state particle of this process would have to be detected event by event using the forward powered detectors. Each of these events is produced with either protons, neutrons, photons, or any combination of them, depending on the excitation energy. In this table, listed the ratio of the events include different species of the produced particles. So all the events will produce either neutrons or photons. BEAGLE is a general purpose EA generator used to understand the physics and the detector design for EA collisions at EIC. It is based on the PCR6 model to simulate the primary electron and nuclear interactions. The intranuclear cascade process is handled by DPM jet. Finally, the FLUCA model is used to describe the breakup of the nuclear remnant. We have tuned the BEAGLE parameter with the experimental results. We tune the PCR parameter by Zeus, positron, and proton data. The CAS on the event level is shown as here. And the left plot is the B versus the XL distribution. Here, the XL is the momentum fraction carried by the outgoing leading proton. B is obtained from the middle small plot. In the middle small plot is the double differential cross section of leading proton as a function of PT square. Was started in several XL beam. This one is XL is beam is from 0.95 to 0.98. The line is the result of a fit with this function. So B can obtained from the fit in beams of XL. The bands represent the systematic uncertainty. So in the left plot, the black point represents the result from Zeus, and the red squares are the result from PCR and the LPS acceptance. The LPS is a leading proton spectrometer. It's used to accept the leading protons. LPS acceptance here means the LPS trigger conditions and acceptance were required. It needed to drop the tracks very close to beam line or the edge of LPS detectors. And in the PCR result, we also do a roughly cut here. And the red plot shows the comparison of the leading proton production rate as a function of XL. From this plot, I want to show you we have a good PCR tune for the target fragmentation for EP collision. In slide 5, I will show you how well we have validated the BEAGLE results. We use the result from BEAGLE data sample compared with the E65 collaboration muon-xenon target experiment. This plot are all for the inclusive variables, the nu, the q square, the w, and the x broken comparison. In all the plots, the red points represent the result from BEAGLE, and the black open circles are the distribution from E65 data. The ratio of BEAGLE divided by the E65 result is shown in the bottom of each plot. The comparison shows that the BEAGLE does reasonably describe the lepton-nucleus interaction as the EIC. In slide 6, the layout of the far forward region of IR in the hadron going direction is shown. The green rectangle boxes are the dipole magnets. The green cylindrical boxes are the corpus focusing magnets. And the gray tube is a simple representation of the beam pipe. There are 4 far-forward detectors are considered in the current study. The first one is a B0 silicon tracker. It consists of 4 evenly spaced silicon planes in the bore of the B0 PF dipole. It is outside the hadron beam pipe. The second detector is of momentum detector, OMD. It is located after the B1A APF dipole. It is also outside the beam pipe. The off momentum detector is used to tag in the protons from the nuclear breakup that have a rigidity different from that of the nuclear beam. The third one is the Raman pulse detector. It is used for tagging the scattered protons or light nuclei with small scattering angle. It is inside the beam pipe. Finally, we have the 0-degree calorimeter, ZDC. It is used for tagging the neutrons from nuclear breakup. More details you can find in the yellow report. The scattering angle versus the total momentum for protons, neutrons, and photons in big generator are shown in slide 8. The guideline are the approximate acceptance for detecting each particles. The neutron have a good acceptance, close to 95% with the average of 5 millirad of the scattering angle. For the proton, the acceptance is generally very good, except at a very large scattering angle and at very low momentum. The 3 different photon detectors cover almost the entire phase space in the scattering angle up to 22 million radians. Because of the rigidity change, the Raman pulse contribute only less than 1%, but the off momentum detector accept almost of the protons, accounting for 42%. Only 24% of photons are within the ZDC angular acceptance. Most of the photons are currently outside the ZDC. So we finally also simulate a pre-shower within the B0 acceptance to detect the photons. We simulated the pre-shower consists of a light layer and a silicon layer. Assume it posited also in the B0 PF dipole after the B0 silicon tracker. For returning the incoherent events, only one of the particles that is detected by the detectors is sufficient. We put the event goes through the interaction region far forward magnet detectors by ESC route and jump 3. The beam pipe is broken into sections to make it a bit easier to turn pieces on and off inside the simulation. And also it's easy to learn the impact of each section of the beam pipe. We said
this is just your 5 minutes warning. Thank you.
Oh, okay, thank you. We said all the material of the beam pipe is aluminum. The impact of the different detector is started by adding one cut after the other. First step is to wait to neutron in ZDC. This means in one event, if there is at least one neutron hit the ZDC, then remove this event. V2 is on top of V1, also V2 the proton in Raman pulse. V3 is to add the proton in off momentum detector. V4 is in addition to V3. We also add a cut of no proton in B0. The procedure of the V2 process is illustrated in the left plot. Is the survived events T distribution after each step. The survived event counts after each step is listed in the right table. By weakening neutrons and protons, the total rejection fraction is to be around 85%. And in the finger, the double arrows and the horizontal bars present the position of the minimum of the diffractive pattern based on theory. The difference between the upper and the lower bar is the difference assuming saturation and a non-saturation model. So based on the current forward detector setup and the BIGO model, there are at least 1 to 2 orders of the magnitude more separation is needed for clean measurement. In order to further surprise the incoherent contribution to a level that at least below the 3 millimole position of the diffractive pattern, we continue to veto photon. As I said previous, we also simulate a pre-shower, which consists of a lead plate and a silicon plate. It is within the B0 AF magnet bore. We also veto the photon converter particles in pre-shower. And veto photon within more than 50 MeV energy in ZDC. After all these cuts, there are still 5.8% event survived, like the blue solid line shows. But the rejection power is still not enough. We also studied the material impact of the beam pipe to this study. We changed the beam pipe around the Raman pot and ZDC from aluminum to beryllium and stainless steel. So we can see the vetoing power with the beryllium is basically same as with the aluminum, but with the stainless steel is the vetoing power is worst. In order to surprise the incoherent contribution, we further required to veto the particles in the main detector. We don't have the joint simulation for the main detector, but we try to veto the particles other than scattered electron and the JEPSI in the main detector acceptance to see what impact it does on the veto. In this slide, the impact of this step is shown as the red solid curve. So with this requirement, the survived event is still 5.69%. However, the rejection power is still not enough to reach the 3 minimum positions. At last, I will close with a summary. The coherent vector meson production is a very important but challenging measurement. And from the comparison between the BIGO and the experimental data, it is tuned successfully to several different measurements. The vetoing power of incoherent events depends on the overall far-forward acceptance and the beam pipe design and the material impacts the and the material also impacts the vetoing power. The careful optimization from the calorimeters and beam pipe design is underway. That's all my presentation. Thank you for your attention.
Thank you very much for your study of coherent and incoherent vector meson production at the EIC and how this is all related with the beam pipe design and the forward detection. We have time for one question. Is there a question? I don't see anything, so let me shortly ask one. You mentioned in your second point that that you tuned Beagle. Beagle, as a benchmark generator for EA simulations, is really important for the EIC simulations. What do you think would be required for further developments of Beagle to tune it even better for EA studies?
Actually, we only use we tune the Beagle result only with the E65 E65 result muon-Zener collision. The comparison shows the Beagle actually does reasonably describe the lepton nucleus interaction as a EIC. But I know there are also a lot of things need to be improved at Beagle. And we are also, more improvement is also doing under the way.
Thank you. Thank you very much for the studies and this overview. So we're coming for the last talk of the morning session, and we will now hear about the upcoming SpinQuest experiment at Fermilab by Mikhail Yurov. Similar as previous speakers, I will give you a 5-minute warning, and I'm looking forward to your presentation.
Hello, can you hear me?
Yeah.
Can you see my slides?
Yes, also see slides. You're ready to start.
Okay, thank you, and thank you to organizer for giving this opportunity. Today I'm going to talk about Fermilab E1039 SpinQuest experiment with transversely polarized target, which is the only high statistics experiment designed to make a measurement of the C-quark Sivers asymmetries. And it's not some distant future experiment. We actually we hope to start data taking maybe even this summer, and the preparation for this experiment are happening now as we speak. And in this talk, I'm going to present the motivation behind the experiment, the current status, and we'll conclude with the installation and commissioning schedule. So we see a lot of efforts put in the nucleon structure exploration, and particularly in resolving its full three-dimensional structure. The TMDs encodes this three-dimensional view of the nucleon in the momentum space, and just based on today's presentations, we see that this program is very broad and very rich. And here's the familiar table that lists all leading twist TMDs, PDFs according to the polarization of the quark or a nucleon, and among 8 leading TMDs, there is a Sivers function, which was also mentioned today in several talks. It represents transverse momentum distribution of unpolarized quarks and transversely polarized proton. And it was introduced by Sivers in the 90s, was proposed to explain results of several polarized experiments which observed the symmetry at large transverse momentum and polarized hyperon and pion production. And one of the important features of TMD is that they offer a link to the orbital angular momentum contribution to the nucleon spin. And our current experimental data and theoretical calculations indicate that even after accounting for quarks, anti-quarks, and gluon spin, we're still missing about half of the proton spin picture. And there is currently significant experimental efforts at Compass, JLab, and other facilities to improve understanding of the valence quark orbital angular momentum contribution to the proton spin. But the contribution of the C-quarks to this picture remains mostly unexplored. And some lattice calculations indicates that C-quarks orbital angular momentum could be actually a major part of the missing spin. And even though that there is no established model independent connection between TMDs and LQ bar, the observation of non-zero C-quark Sivers asymmetry would mean that the C-quarks have non-zero orbital angular momentum and that they do contribute to the proton spin, which would be quite significant discovery. And SpinQuest collaboration focuses on exploring the role of C in this picture by investigating the correlation of the light anti-quark motion relative to the nucleon spin. So, and our program is built upon and is an extension of a family or a series of Fermilab experiments that explored nucleon's anti-quark content for many years now by measuring its flavors asymmetry in a wide range of X values. On the left here, you can see the results of Fermilab E866 experiment, or μC, that measured the strong D bar over U bar enhancement, while previously the C-quark momentum distribution was naively believed to be symmetric. And the yellow squares on the right figure represents the results of SeaQuest E906 Fermilab experiment, which were very recently published in Nature, and the SeaQuest was designed to investigate the flavor asymmetry at higher compared to μC X values. And you can see that the μC results on the left suggest that the ratio of D bar over U bar began to decrease here with a higher statistical uncertainty, obviously, for the X values greater than 0.2. And as can be seen from these pictures, the trend between the two experiments at higher XT are quite different. And so no explanation has been found yet for the different results. And if you're interested in the SeaQuest analysis details and its conclusion, I encourage everyone to attend tomorrow's K-Nagai talk. It's going to start around 9 a.m. tomorrow morning. And so we have a number of calculations that make quite similar predictions on the D bar over U bar X dependence, including the meson cloud and statistical models shown in cyan and greenish bands. And so the SpinQuest with or how we call it, polarized SpinQuest experiment with the Sivers function measurement is just a natural continuation of this program to test validity and help distinguish between these various models. Several global Sivers function extractions exist, and they are mostly based on the Hermes, Compass, JLab, and STAR data. This data includes results of semi-inclusive scattering and Drell-Yan production. And even though the quality of these feeds are continuously improving, the Sivers extraction for anti-quark remain mostly indirect and poorly constrained. And some estimates show a possible flavor dependence in the C-quark Sivers asymmetry, and that is important to observe these things directly. So experimentally, Sivers function is investigated in semi-inclusive deep and elastic lepton nucleon scattering and in polarized Drell-Yan production experiments. In CDIS measurements are complicated by the fact that the Sivers function is convoluted with fragmentation function, while Drell-Yan allows direct measurement of the Sivers function without the complication of the final state interactions. Drell-Yan also features a very good anti-quark selectivity by kinematical means with only small background from other quark combinations, while in CDIS, one measures the mixture of the valence and the C-quark states. So accessing the C-quark Sivers function through Drell-Yan production hasn't been tried before. And this table on the left schematically shows that the valence quark Sivers function are relatively well known thanks to the CDS measurements and CDS measurements at Hermes, at Jefferson Lab, and ongoing efforts at Compass. But for the C-quark Sivers function, CDS has poor sensitivity, and C-quark brilliance is mostly unexplored. And as I said, E1039 can kinematically select contact quark from target. So this second term here is almost negligible. And also by exploding a proton and deuteron target, E1039 can measure asymmetry for both U bar and D bar. So that means that we can possibly determine Sivers flavor dependence of the C-quarks. So in summary, the experiment intends to measure the sign and the value of C-quark asymmetry, possible Sivers flavor dependence, and if non-zero asymmetry will be observed, it would be a clear evidence of the C-quark orbital angular momentum. The plot on the right shows expected experimental uncertainties, basically our sensitivity, along with the asymmetry estimates from two predictions. These predictions were available at the time of the proposal, and the calculations that you see here are shown only for, are done for NH3 target or the proton target only. There are more recent calculations exist. They indicate a smaller asymmetry, but again, experimentally, all of these predictions remain mostly unconstrained.
You have 5 more minutes.
Yes, and I will switch to the description of the experimental setup a little bit. So we're going to use 120 GeV unpolarized proton beam from Fermilab main injector directed into one of the fixed target beam line. The beam has this characteristics, is basically a 4-second spill in 1 minute with 53 megahertz substructure, and we expect that number of the protons on the target in 1 year. The actual beam intensity will be determined by a quench threshold of the superconducting magnet in the polarized target system, which I will show in a second. So the produced diamuons are detected in E906 muon spectrometer. This spectrometer includes focusing and analyzing magnets, drift chambers, proportional tubes, and scintillation photoscope form for measuring station, as you can see here, and provide muon tracking and triggering. And below you can see expected kinematic coverage and schematic view of the typical dimuon event observed in the spectrometer. A small Drell-Yan cross-section is one of the major experimental challenges, and which is why we choose a thick, highly density and highly polarizable fixed target for E1039 physics goals. The optimum choice to satisfy these needs was usage of the solid ammonia and deuterated ammonia targets, which can routinely achieve over 90 and 40% of proton and deuteron polarization respectively. The polarization in this type of targets is achieved through so-called dynamic nuclear polarization mechanism, and for that we need a suitable material doped with paramagnetic radicals. They're normally placed in a high magnetic field, cooled down to low temperature, and under these conditions, the electron polarization is nearly 100%, and electron polarization then can be transferred to the nucleus through electron-proton spin coupling. And this desired spin states can be selected by irradiation with the microwave of appropriate frequency. And important features of the E1039 target is 8 centimeter long cups, 5 Tesla magnet, 1 Kelvin for helium for evaporation for each, and NMR system that can maintain up to 9 NMR channels. What is the current status of the experiment? As I said before, SpinQuest is a successor of the CQuest experiment, but E906 or CQuest setup had to go through a number of serious infrastructure modification. Major innovation of the experimental setup is the usage of the polarized target, which I just mentioned, and that dictated many changes to the experimental hole and the whole setup. We have to design and construct a new collimator to protect the target magnet from quenching on residual beam halo. A new target cave and cryo platform for the target infrastructure has to be constructed, which is shown schematically here. And the target subsystem residing on the top of the shielding blocks, for which a new radiation environment and simulation has been done. And the spectrometer is located behind the target. And here you can see a view from the back of the spectrometer in the upstream direction. Some spectrometer upgrades include development of the dedicated VERSEP trigger, dark photon photoscope construction for a parallel physics program, and also GPU-based fast online reconstruction to improve the quality of the data taking. Oops. Developing the polarized target system was a 4-year-long effort. It was a major effort of Los Alamos National Lab and University of Virginia. You can see the schematic view of the system. It also went through a major upgrades, such as rotation of the magnet coils to get the proper field direction. New target inserts were built at University of Virginia. And there are a number of different other modifications. One of the conditions from DOE was that the helium gas has to be recirculated and not wasted during the operation. So the construction of the helium liquefaction plant with a capacity of about 200 liters a day was contracted to outside contractor. It's a company, Quantum Technology, and the system installation is nearly complete, which you can see on this photo. And we are completing that setup. Another major effort for this experiment was developing of a new NMR system for polarization measurement that replaces gradually retiring Liverpool Q-meter, normally used for this type of a target. And the new system has opportunity to and several improvements which would help to reduce polarization-related systematics. And this is the current timeline of the experiment. The commissioning of the previous experiment was done in the beginning of 2018. We received the stage 2 approval in May of 2019 and shipped the target to Fermilab in the middle of 2019. And a lot of work has been done since then to verify spectrometer performance. And we are currently installing remaining cryogenic infrastructure so that we can connect the target system with the liquefaction plant. And we hope to do initial beam commissioning in this fiscal year, with the idea of starting data taking in 2022. And we approved to run for 2 years, and with hopefully producing very exciting physics results. And in a summary, to conclude, I would like to say that the main goal of SpinQuest experiment is to measure Sivers asymmetry for both U-bar and D-bar quarks, and observing such asymmetry would be a smoking gun evidence for non-zero orbital angular momentum of the C-quarks, which is quite exciting, would be quite exciting news. And what I didn't mention, that E1039 also allow for many other interesting opportunities with possibility of a large physics payoff. And we are very close to start beam commissioning and production data. So if you're interested in this type of physics, now is a perfect time to join SpinQuest collaboration, and we would be happy to welcome new members. Thank you.
Thank you very much for your introduction to SpinQuest and the status report. I didn't give you the 15 minutes warning, but you are at the 18 minutes of your talk. let's have short questions. Luciano, please.
Yes, so very nice talk. Just a question, a curiosity maybe. So your physics program is concentrated on the Sivers function, but of course, with your setup, with your transverse target and your proton beam, you can also get for free access to the transversity function for the C up and outward, and maybe also access to the Bohr-Mulder from the unpolarized beam as well. So are you planning to extend your program beyond the Sivers function? Or?
Exactly. That's what I said in the beginning, that I didn't mention all other possibilities. And as you said, we can for free try to access Bohr-Mulder, which is actually CQuest is also capable. Like CQuest was unpolarized experiment, so they also can do that extraction too, and they're working on that. And we can do basically for free Sivers, transversity, and Bohr-Mulder, but major focus is the Sivers function. The proposal was written for the Sivers function. There is also some other opportunities, such as exploration of the dark photon search and J-psi, possible J-psi asymmetry. So yes, it's quite a lot can be done in this experiment.
So even so, we are 5 minutes already in the coffee break. I would like to allow the last question by Caro, and then we will conclude the session.
Thank you for allowing me. I would like to ask how often you're planning to switch between the NH3 and ND3 target, how often you plan to repolarize, and if you also plan to have nuclear targets in addition to the transversely polarized target.
It's a very good question. So first of all, during commissioning, we have to see what would be the quench threshold for the target magnet. And so that will define a lot of optimization for the run plan. So for the current run plan, we hope to run kind of 50-50 for NH3 and ND3 targets. Most recently, experiments with this type of target were done at Jefferson Lab, which is a continuous electron beam, and here we have a pulsed, not pulsed, but the proton beam, which has like a 5 spill window, 5 second spill window, and basically we are not sure how fast the NH3 will depolarize, but estimates right now is that we would have to do anneals every day and maybe exchange of the target every week or so. So it's hard to predict how often we will have to switch between the NH3 and ND3 targets, but so right now we plan to have 2 cups filled with one with NH3, one with ND3, and if everything is good, then we will be switching them right away. If the threshold, quench threshold is too low, then maybe we will be running with NH3 target only. So that I cannot answer right now. And yes, there is a place on the target letter for additional targets or for the empty spot to do the background checks. But I'm not sure. I don't think like that we seriously discuss of using nuclear targets so far. I think we're now focusing only on NH3 and ND3 targets.
Could be very interesting for nuclear as well. Yeah. Thank you.
Yeah.
So thank you very much. That concludes the first session of Future Experiments and Facilities. We continue in 6 minutes with the second session. Thanks for all the speakers, and thanks everyone for the discussion, and also the understanding that we had to limit the discussion time. Thank you. Talk to you in a few minutes.